In question number 16, in a single slit diffraction, the width of the slit is 0.5 centimeter. The focal length of the lens is 40 centimeter, that is capital D is equals to 40 centimeter, and the wavelength of light is 4890 angstrom. We want to find the distance of first dark. Here it is given that we want to find the first minima. A sin theta is given as n lambda. Here it is d sin theta, and sin theta is also given by x1 by focal length. So x1 will be equal to focal length into lambda divided by d. So x1 is equals to focal length is 40 centimeter, that is 4 into 10 power minus 2. Lambda is 4890 into 10 power minus 10 divided by d is 0.5 centimeter. So x1 will be equal to 3.912 into 10 power minus 5 meter. So it will approximately be 4 into 10 power minus 5 meter. So option 2 is correct option. In question number 17, the angular width of central maxima is pi by 2. When a slit of width A is illuminated by a light of wavelength 7000 angstrom, we want to find this slit width A. Here the angular width of central maxima, that means if this is point, then this angle will be theta, and that is equals to pi by 2. So this half angle will be pi by 4. So for minima we can write A sin pi by 4 is equals to lambda. So A will be equal to lambda divided by sin pi by 4, that is 1 by root 2. So A will be equal to 7 into 10 power minus 7 into root 2. So A will be equal to 9.8 into 10 power minus 7 meter. So option 4 is correct option. In question number 18, the sun subtends an angle of 1 by 2 degree on the earth. The image of sun is obtained on the screen with the help of a convex lens of focal length 100 centimeter. We want to find the diameter of the image obtained on the screen, that is x. Here the subtended angle is 1.2 degree. So from this we can write angle theta is equals to arc upon radius. Here arc is x and radius is f, but this theta should be in radian. So pi by 180 into 1 by 2 is equals to x by f. So x is equals to 100 into pi divided by 360. So x will be approximately 8.73 mm. So option 4 is correct option. In question number 19, the limit of resolution of microscope we want to find. The numerical aperture of microscope is 0.12 and the wavelength of light used is 600 nanometer. The limit of resolution is given by x is equals to lambda by 2 into NE. Lambda is 600 into 10 power minus 9 divided by 2 into 0.12. So x will approximately be equal to 2.5 micrometer. So option 3 is correct option. In question number 20, the least resolvable angle by the telescope, that is, we want to find the aperture 5 meter and the wavelength of light used is given 4000 angstrom. The minimum angle for microscope is given by theta minimum is equals to 1.22 lambda by d. So theta minimum will be equal to 1.22 into lambda will be 4 into 10 power minus 7 divided by 5, but this will be answer in radian. If we convert it in second, theta minimum will be 1 by 50 second. So option 3 is correct option. In question number 21, the wavelength of light used in an optical instrument are lambda 1 is equals to 4000 angstrom and lambda 2 is equals to 5000 angstrom. We want to find the ratio of the respective resolving powers. The resolving power is inversely proportional to lambda. So RP2 or RP1 by RP2 is equals to lambda 2 by lambda 1, that is equals to 5000 divided by 4000. So RP1 by RP2 is equals to 5:4. So option 4 is correct option. In question number 22, the angle of incidence at which reflected light is totally polarized for reflection from air to glass is given by. Here, the angle of incidence at which reflected ray is totally polarized is called angle of polarization, and according to Brewster's law, 10 IP is equals to N. So IP will be equal to 10 inverse of N. So option 4 is correct option. In question number 23, a light ray is incident on a transparent medium of refractive index 1.732, that is equal to root through at the polarizing angle. We want to find the angle of refraction. Here 10I will be equal to mu, that is equals to root 3. So I is equals to 60 degree. Now applying Snell's law, sin I is equals to mu sin R. Sin I, that will be root 3 by 2 is equals to root 3 sin R. So sin R will be equal to 1 by 2. From this we can write angle of refraction is equals to 30 degree. So option 2 is correct option. In question number 24, a ray of light in air is incident on a glass plate at polarizing angle of incidence. It suffers a deviation of 22 degree on entering the glass. So delta is equals to 22 degree. We want to find the angle of polarization. Here, if we apply Snell's law, then sin I is equals to mu sin R, and it is given here that R is equals to I minus 22 degree. So sine I divided by sine R is equals to mu. So sine I divided by sine of I minus 22 is equals to mu. But mu can be written as tan of polarizing angle, that will be equal to sine I upon cos I. So cos I will be equal to sine of I minus 22. So sine of 90 minus I is equals to sine of I minus 22. From this we can write 90 minus I is equals to I minus 22. So I will be equal to 56 degree. So option 2 is correct option. In question number 25, the critical angle for the total internal reflection for the substance is 45 degree. We want to find the polarizing angle for that substance. Here, for any substance, the critical angle sin C is given by 1 by mu. So mu will be equal to 1 upon sine 45 degree, that is equals to root 2. But according to Brewster's law, tan IP is equals to mu, that is equals to root 2. It is given in the question that tan 54 degree and 44 minute is equals to root 2. So IP is equals to 54 degree and 44 minutes. So option 2 is correct option. In question number 26, unpolarized light of intensity I0 is incident on a polarizer and the emerging light strikes a second polarizing filter with its axis at 45 degree to that of the first one. We want to find the intensity of the emerging beam. There are two polarizers. One is at 45 degree. The second one is at 45 degree with the first one. When light of intensity I0 is incident on first polarizer, the intensity coming out will be I0 by 2. So the transmitting intensity is given by I0 by 2 cos square theta. Here theta is given 45 degree. So I transmitted will be I0 by 2 into 1 by root 2 whole square. So I transmitted will be I0 by 4. So option 2 is correct option. In question number 27, the axis of the polarizer and the analyzer are inclined to each other at the angle of 60 degree. The amplitude of polarized light emergent through the analyzer is A. We want to find the amplitude of unpolarized light incident on the polarizer, that is A naught. Here we know the relation between intensities. The intensity coming out of the analyzer will be I0 by 2 into cos square theta. So I will be equal to I0 by 2 cos square 60 degree. Cos 60 is 1 by 2. So I will be equal to I0 by 8. Now we know that intensity is directly proportional to amplitude square. So I by I0 is equals to A square by A0 square. So A naught square will be equal to A square into I naught divided by I. But from this we can write I naught divided by I is 8. So A naught square will be equal to 8A square. So A naught will be equal to 2 root 2A. So option 4 is correct option. In question number 28, unpolarized light of intensity I is incident on a polarizer and the emerging light strikes the second polarizing filter with its axis at 45 degree to that of first. We want to determine the intensity of the emerging beam and its state of polarization. The intensity of emerging beam is given by I dash is equals to I by 2 into cos square theta. Here theta will be 45 and that is equals to 1 by root 2. So 1 by root 2 whole square. So I dash will be equal to I by 4. And it will be parallel to the second filter. So option 1 is correct option. In question number 29, a parallel beam of width A is incident on the surface of glass slab having refractive index 3 by 2 at an angle I and the angle of refraction is R. Now the width of the refracted parallel beam will be, we want to compare these two widths given D is equals to A. Here from this geometry we can write cos R is equals to D dash upon PQ. So D dash is equals to PQ cos R. Now cos I is D upon PQ. So D is equals to PQ cos I. Now applying Snell's law, we can write N1 sin I is equals to N2 sin R. So sin I will be equal to N2, that is 3 by 2 sin R. So sin R divided by sin I is equals to 2 by 3. Now D dash by D is equals to PQ cos R divided by PQ cos I, that is equal to cos R divided by cos I. So we can write D dash is equals to D, that is equals to A cos R upon cos I. Now as sin R is less than sin I, cos R will be greater than cos I. So as cos R is greater than cos I, this ratio will be greater than 1. So we can write D dash is greater than A. So option 3 is correct option. In question number 30, when a parallel beam of monochromatic light suffers refraction while going from rarer to denser medium, which of the following is correct? Here we have just seen in the previous question that when the light goes from rarer to denser medium, the width of beam increases as D dash is greater than D and the refracted angle will be more than angle of incidence. So in this case, statements B and C are correct. So option 4 is correct option.